Today, we are exploring one of the simplest kinds of computers, the finite automata, a model so elegant that it can recognize infinite languages and still fit on a whiteboard. Welcome to Fully Attributed. Let's say you had to design a machine to detect if a string of input bits contain two ones in a row. Now, the simplest machine that is able to solve this is called a finite state machine, or a deterministic finite automata, DFA in short. Here's a DFA that solves our problem. But how does this machine even work? Well, it has three states, represented in the state diagram as Q1, Q2, and Q3. The arrow coming from nowhere shows that Q1 is the start state. Every state has two outgoing arrows to other states that are labeled with ones and zeros. And the double circle around Q3 means that it's an accept state. Since this machine only works on binary input, we say its alphabet is the set 0 and 1. Here's how this DFA works. Before reading anything from the input, it starts at the start state. It then reads the input one symbol at a time. If it reads a 1, it goes to Q2. If it reads a 0, it goes back to Q1. It keeps doing this. It keeps moving between states until it runs out of input. If the final state is an accept state, we say that the machine accepts the string. And if the final state is not an accept state, we say that the machine rejects the string. And we now have a detector for our problem. And even though this DFA has only three states, it can recognize any string that has two ones in a row. And there are infinitely many such strings. Take a moment to digest that. Every string that this DFA accepts is part of its language. What is a language? It is just a set of strings. So, the language that this DFA recognizes can be described as the set of strings that contain two ones in a row. This was just one example of a DFA, but you can build many others to recognize all sorts of languages. For instance, here's a DFA that accepts strings with all zeros appearing before all ones. And here's one that accepts only strings that start with 0, 1, 0. Note the reject states in both of these. If the machine somehow reaches this state, it will never accept the input. You'll see this reject state often in a lot of DFAs. But now you may wonder, can the simple model recognize every possible kind of string? The answer to that is no. Why? Because this machine has no memory. It can't keep a track of how many symbols it has seen before. It only knows what state it is in right now and where it can go next by reading the next input symbol. Consider this language, for example, where there are an equal number of zeros before ones. Basically, 0 to the power n, 1 to the power n, where n is an integer. You can't build a DFA to recognize this language, because that would require the DFA to count how many zeros were seen, but it can't do that because it doesn't have a counter. In fact, if you can construct a DFA, the set of strings that it accepts, that is, its language, is called a regular language. Here are some examples of regular languages. And if for a language you cannot make a DFA, then those languages are called non-regular languages. You may have heard of regex or regular expressions before. Well, a regular language can also be described using a regular expression. In fact, that's actually where the name comes from. Here's the regex for the languages we've seen before. Let's focus on the first one. The star here is called the Kleene star operator, which means that there should be 0 or more occurrences of the group before. This pipe symbol here means OR. So this part of the regex means any number of zeros and ones, followed by two consecutive ones, followed by any number of zeros and ones once again. The regular expressions we use in programming today, however, aren't purely regular anymore. They have evolved way beyond what finite automata could do, with features like back references and lookaheads that let them handle non-regular patterns. So technically, modern regex isn't really regular, but that's a story for another day. So in just a few states, these machines can recognize so many different patterns, and that's the beauty of finite automata. They're simple, elegant, and yet powerful. But what if we gave our machines memory? That's where pushdown automata come in, and we'll explore that in a future episode of Fully Attributed. Thanks for watching. If you enjoyed this video, make sure to like and subscribe, and I'll see you in the next one. Goodbye.